Students, in the previous video we have discussed about the moment of inertia of a triangular lamina as well as the triangular lamina as well as the rectangular lamina. So now we shall move for the moment of inertia of a circle here. So just observe, this is what a circle. You just consider the strip here. So the hollow strip you have considered here, which is having the thickness is dx. You can observe here the thickness of this strip is ds, and the strip having the radius of x, and the total entire circle is having the radius is r. So now you need to find out what is the second moment area or the moment of inertia of this circle about x-axis, that is ixx. You need to find out. So one more thing, for a circle, we are having the moment of inertia for both x and y axis are similar because we are having the radius. The radius is similar for all the circle. Therefore, the moment of inertia, that is ixx, is always equal to the iy bar also in case of what the circle. So let us see the moment of inertia derivation here. So let us consider. The circular lamina of radius r. This is the circular lamina which is having the radius r as shown in figure. So now let us show the circular elementary strip of thickness dx at a distance of x from the center. So this is what an elementary strip, whatever the hatched portion is there, elementary strip which is having a thickness is dx. Clear? That is dx is the thickness. So from the center it is having the radius of x, it is the radius x is there. So now the area of this elementary strip you need to consider. So that is area of the elementary strip is nothing but, so here since it is a hollow section is there, so you need to consider 2 pi r, that is perimeter into thickness will be the area here. So the perimeter into thickness will be the area here. So that is area of the elementary strip is equal to perimeter is 2 pi, r is nothing but this x is the radius into dx. Dx is what? Thickness. That is what the area of this elementary, that is hollow strip you have considered. Therefore it is thickness into perimeter will be the area, that is area of the elementary strip you have considered. So now moment of inertia about z axis. So here x and y you are considering the moment of inertia to the perpendicular plane you are considering, that is about z axis you need to consider. So that is area into perpendicular distance. Area is 2 pi x into dx, that is 2 pi x into dx, into the perpendicular distance is what? X, that is square of the perpendicular distance, and it is a moment of inertia. So that is 2 pi x into dx into x square is the your moment of inertia about z axis. So now the whole area, the whole circle, so this is for the single strip. The moment of inertia about z axis, that is for the single strip is what? 2 pi x dx into x square. So if you want to calculate for the whole strip, so then you have to integrate. So under what limit you are going to integrate here? Since it is a circle, it is having a radius r, therefore you need to integrate under the limits of 0 to r. You just observe this highlighter, that is 0 to r, under the limits you need to integrate here. So this is what the elementary strip, moment of inertia of elementary strip, that is about z axis. Just substitute here, integrate under the limits of 0 to r here. So 2 pi is constant, you need to integrate with respect to the dx, therefore x cube integration is x raised to 4 divided by 4. Just substitute, integrate and apply the limits, you will get the iz is equal to what? Pi r raised to 4 divided by 2 here. So this is what moment of inertia about the z axis, but we need moment of inertia about the x axis or y axis, that is ix bar and iy bar we need. Clear? So as I told, for a circular lamina the moment of inertia for x and y axis are same, that is ix bar is equal to the iy bar. Therefore what you need to do here, we are having the equation from the perpendicular axis, iz is equal to ix plus iy bar. So the perpendicular axis we have derived this equation, that is iz bar is equal to ix bar plus iy bar. So what the perpendicular axis theorem says, so if we are considering a moment of inertia of any perpendicular plane, so which is equal to the summation of the moment of inertia of the two mutually perpendicular planes. So that is what the perpendicular axis theorem. So by this perpendicular axis theorem, we are having Iz is equal to Ix bar plus Iy bar. So but we are having the Iz equation here. Just substitute the Iz equation. Ix and Iy are same for the circle, therefore it is 2Ix bar you need consider. Therefore Iz is known, you just bring this 2 to the denominator. Therefore Ix bar is equal to this equation, that is pi r raised to 4 divided by 4 is the moment of inertia of a circle. Clear? Ix bar is equal to Iy bar is equal to pi r square divided by 4 is what your moment of inertia of the circle. You just observe here. So this is what the moment of inertia of a circle. So let us see the moment of inertia of the semicircle. So there is no much difference here. So some calculation you need to do for the semicircle. Just observe here. The moment of inertia of this semicircle you need to consider. So this is what the semicircle we have considered. So now consider the semicircular lamina which is having a radius. Again, if it is a semicircle also radius is same r. So now the moment of inertia of a semicircle about the diametrical axis. Diametrical axis is nothing but what? AB. So about the diametrical axis is equal to what? Off into moment of inertia of the circle they have considered. Moment of inertia of the circle is what you have just derived, that is pi r raised to 4 divided by 4 is the moment of inertia of a circle. So moment of inertia of the semicircle is nothing but half of the circle. It is about the diametrical axis is what? So that is half into moment of inertia of a circle. Therefore pi r raised to square divided by 8 is the moment of inertia of this semicircle about the point AB. Is it clear? About the point AB is what? But we need Ixx, that is Iyy. Ix bar and Iy bar we need. So that is moment of inertia about x axis as well as moment of inertia about y axis we need. So therefore by the parallel axis theorem, clear? By the parallel axis theorem, the moment of inertia of any axis which is exactly parallel to the centroidal axis, you can observe in the figure. AB is the, you have considered any axis as in 1 1 in the derivation. Here we have considered the AB. And the centroidal axis is this x dotted line. This is the centroidal axis. Y, the dotted line is also centroidal axis. So by the parallel axis theorem, what the parallel axis theorem says? The moment of inertia of any axis which is parallel to the centroidal axis, AB is also parallel to the centroidal axis, is equal to the moment of inertia of the entire area about the centroidal axis is nothing but Ix bar plus area into square of the perpendicular distance, that is y bar. That is what a parallel axis theorem. So we are having the parallel axis theorem and we are having the moment of inertia about AB or at any axis we are having. So by this you can take Ix bar outside, then IB minus area of the semicircle is known. What is the area of the semicircle? Pi r square divided by 2. Just substitute area, and y bar for a semicircle. Y bar is nothing but what? The centroidal distance. The centroid of a semicircle. We know that centroid of a semicircle is what? That is if it is lies in a first quadrant, you just go through the centroidal formulas. The centroid of a semicircle is what? If it is a d and if it is a r, that is x bar is nothing but this distance. Centroid of a semicircle, that is x bar and y bar is there. Y bar, that is 4r divided by 3 pi. So if you got confused, you just go through the formulas of centroid. Y bar is nothing but 4r by divided by 3 pi. Just do the simplification. That is moment of inertia of AB, you just substitute, and remaining things you have to substitute to do the simplification here. So by the simplification you will get the Ix bar is equal to 0.11 I into r raised to 4. So this is what the moment of inertia of this semicircle. Then similarly the moment of inertia about the y-axis. So this is about the x-axis. The moment of inertia about the y-axis is directly off of the moment of inertia of the circle. That is moment of inertia of the circle what you have considered, this is pi r raised to 4 divided by 8 is the moment of inertia about the y-axis. 0.11 r raised to 4 is the moment of inertia about the x-axis here. So this is what the moment of inertia for the different geometrical figures what we have discussed. So still no. So now from the next sessions we will move for how to solve the problems that is on the moment of inertia problems of the different geometrical figures. Thank you.